Welcome to the next video in Discrete Math. This is video 1, where we're going to introduce the problem called the Tower of Hanoi, and it corresponds to Chapter 1, Section 1 of the textbook. So let's start with a description of the problem. We have this children's toy, and it is called the Tower of Hanoi. It consists of 3 pegs, right? So if you think there's like this board, it's got these 3 pegs, or rods, or whatever you want to call them. Each of them are pointing up out of the board. And there are 8 differently sized discs, right? So at the very top is the smallest one, and then bigger and bigger, and so on. Oh, I guess there are supposed to be 8. I drew 7. Oh, well, you get the idea. So the challenge is to move the stack of all of these discs from one peg to another. Now, just for the sake of specificity, we'll talk about moving them from the first peg over to the third one. But the challenge here, right, there has to be some kind of constraint, otherwise it's not interesting. You can only move one disc at a time. It has to go to one of the other pegs, and you must always put a disc, or let me put it this way, you can never put a bigger disc on top of a smaller disc. Okay, so those are the constraints. Now there is just the puzzle, but then there's also this mathematical question that we can ask. What is the minimum number of moves that you could do to solve the Tower of Hanoi problem? So this is going to introduce a kind of a proof technique, which is, to always, right, if you struggle to think about how to prove something or to come up with an answer to this problem, just think of a smaller version of the problem. And for one thing, right, that can just get you a feel for the problem, right? It'll give you a sense of, the kinds of things to pay attention to, or even just what we're talking about if it takes a little bit of time to warm up to the idea. In some cases, not all, but some cases, in fact, whatever solution you give to the smaller problem, especially if you give a kind of, in some sense, a nice solution to the small problem, then you can actually use that solution for the small problem and apply it to the bigger problem. So that is what's going to happen here. Now, let's think about the situation if there were just a single disc. Well, that's really easy, right? The minimum number of moves, obviously, is just 1, because you pick up that one disc from the first peg, move it over to the last peg. You couldn't do it in any fewer moves than 1, so 1 is the minimum solution. What if there were 2 discs? Well, so you're going to have a disc with a smaller, okay, that looks good enough for our purposes. So a disc with a smaller one on top of it. Now, you can't, right, like move the smallest one all the way to the third peg, so move it to the second peg just to kind of get it out of the way. Take the bottom disc, move it to the third peg. Now that biggest disc is in the correct position, and then you can follow it up with a move for that small disc to go on top of the big disc. There we did it in 3 moves, right? So we know it's possible to do this in 3 moves. It may be a little bit challenging to understand, like how would we argue that it could not possibly be done in fewer than 3 moves? Well, we can kind of just argue by eliminating various possibilities. So for one thing, we could go ahead and say that, well, there's just no way that the first move we do is moving that smallest disc all the way to the third peg. And here's why. Because if we did, we would then have to, for like whatever else is going on, we would have to eventually move it off because, that bigger disc would have to go underneath it, and we'd have to eventually get the small one out of the way. So that's already 2 moves. Well, and we wouldn't have a solution. So there's no way that a solution corresponds to putting that smallest disc in the first move over to the third peg. It has to go to the second peg. Okay, but once that, is there, it has to be that moving the biggest disk over to the third peg is, in some sense, the only right next move that'll get us towards a minimal solution, because that move puts that bottom disk in its correct place, and that has to happen sometime. So that has to be a move that gets us a minimal solution. And so that all right, so we've already said the smallest disk has to go to the second peg to get a smallest solution. The bigger disk has to go to the third peg, and that's already two moves. So we know, right, since those have to happen in order to work towards a minimum solution, and that's already two moves, then there's no way to do it in two moves, right? There's an argument for why this is a minimal. So, right, not just a solution, but a solution of a minimal number of steps. So now that we've done it with one disk and two disks, let's start thinking about how we're going to approach the problem if we have any n number of disks. And this is, by the way, sort of its own proof technique, right? Like when you're challenged with giving a proof all by yourself, and you're thinking, well, what do I do? Often a nice thing to do is to take this, some kind of important part of the problem and to give it a name, right? So so just calling the number of disks n is kind of a natural thing to do, but let's not pass it over without appreciating that this is often something you should do when you get around to doing your own solutions to exercise problems. So anyway, so we're going to say that the number of disks is n. We know our target number is 8, but let's think about the somewhat more abstract setting of just n disks. And you can sort of realize that, well, look, if you think about the n minus 1 disks that are smallest, right? With a kind of thinking of that largest disk at the very bottom as its own separate thing, but you've got n minus 1 disks above it, and we essentially the idea is, well, we would like to be able to move them out of the way, so we would like to move all of them over to the second peg. With them out of the way, we can then take that largest disk, move it over to the third peg, and once that is done, we can take these n minus 1 disks and move them on top of that largest disk. And so the idea here is that to solve a problem of size n in this particular case, if we could just solve a smaller version of the same problem, we could leverage the solution to the smaller problem to help us to solve the bigger problem. It's a common technique, and this is often called recursion. And if you think about everything that we've done so far, well, look, we already know how to solve the problem when n is equal to 1. We even know how to solve it when n is equal to 2. And this strategy demonstrates that, therefore, we have a strategy to solve it when n is equal to 3, right? Because with n equal to 3, we consider the top two disks, use those two, right? Like apply our solution to the top two disks to move everything over to the middle peg. I know when we talked about the solution for n equal to 2, we moved everything to the third peg, but obviously that doesn't matter. Whatever we did to move everything to the third peg, we could kind of just tweak it so that everything moves over to the second peg instead. So anyway, so we can take those top two disks, move them to the middle peg, take that bottom last disk, move it over to the third peg, then take these two disks and move them over to the third peg, and have a solution to the problem. So that's recursion, and that's applying it when n is equal to 3, but because we have a solution for when n is equal to 3, we could do it all over again to get a solution when n is equal to 4, right? So when n is equal to 4, we again take the top three disks, move them over to the middle peg in the way that we know it can be done, because we just talked about that, right? So we know we can move 3 disks, so we move them over to the middle peg. Take the bottom biggest disk, the 4th disk, move it over to the 3rd peg. Take those 3 disks in the middle, move them over to the 3rd peg now, and you have the solution for when n is equal to 4. And you can do it, right, and you can just keep going, right? When n is equal to 5, you use the solution for when n is equal to 4, which we just talked about how we know that can be solved, and so on. So now let's talk about the time, right? So we have a sort of strategy for how to move the disks over from the 1st peg to the 3rd peg when there are n disks. But let's talk about the minimum number of steps, right? That is, after all, our kind of concern here. And the fact that we have this strategy convinces us, oh, and I have a typo here, it should be a -1. The strategy that we just described is a way to solve the problem when we have n disks. And what we said was that we can basically take, a single, right, use the time it takes to solve the problem for n-1 disks, right? So take those top n-1 disks, and whatever minimum time it takes, you do that to move them over to the middle peg. And that's gonna, right, of course, that consumes n-1 steps, right? However many steps that is. We still don't know what that is, but we're getting there, I promise. And so we use up that many steps to take those n-1 disks and move them over to the middle peg. Then we take one more step to take that biggest disk that was still at the bottom of the 1st peg and move it over to the 3rd peg. So that eats up 1 step, and so there's a +1. And then, once that's done, we yet again take all of those n-1 disks that are on the middle peg, move them over to the 3rd peg, again requiring, right, the minimum number of steps that we can manage to do that. And we have now one way to solve the problem, and it eats up this much time, which we could simplify into just 2tn-1 plus 1. So we know that the problem can be solved in that much time, but we don't know if that's the minimum amount of time, right? Because that's one way to solve the problem, but there might be others, and how do we know that there isn't a faster way to solve the problem? So here is an argument for why there actually is no more efficient solution. Now, in whatever solution of any kind, right, you always have to get that largest disk to the bottom of the 3rd peg. Think about what happens right before that move takes place. Well, that, largest disk must be sitting at the bottom of the 1st peg, and the 3rd peg must be empty, so all of the n-1 other plates are on the middle peg, and they have to be stacked, right? Because one of the rules is that small plates go on top of bigger plates, right? So they all have to be stacked from least to greatest on that middle peg. But then how did things get into that arrangement in the first place? Well, to get to that point, we must have taken those top n-1 plates and moved them over to the 2nd peg somehow, and we know that the minimal way to do that is, by definition of what we mean by tn-1, it must have taken tn-1 steps to do that part. So you had to use up tn-1 steps to get those n-1 plates to the middle peg. You use 1 step, you have to, in order to take that largest plate and move it over to the 3rd peg, and then you, from that point, have to use tn-1 steps to get from all the n-1 plates or disks on the middle peg over to the 3rd peg. So, effectively, this is the argument that there could not be a more efficient way to solve the problem. And that gets us the equation that Tn, the minimal way to solve the n-disk problem, is precisely equal to, right? No longer less than or equal to, but now actually equal to 2Tn-1 plus 1. So, okay, great. We have this recurrence relation, or this recurrence equation, as it is sometimes called, right? And so for any given value of n, we can always determine it if we know the value for n minus 1. And we know the value, we know that t1, we've already talked about that, that's equal to 1. And so we also computed that t2 is equal to 3. That's the argument we made earlier. It's nice to check that if we actually followed the equation, would we get the same answer? So let's compute t2, but this time using the recurrence equation. Well, that would tell us that we should use 2t 2 minus 1, right? That n minus 1 here, n is equal to 2. So we're using t2 minus 1 plus 1 from what we already said up above. Since that's the same thing as 2t1 plus 1, and we already know that t1 is 1, right? That's the most basic one, so that one we take for granted, and we can use that here to say that that's 2 times 1 plus 1, and that's equal to 3, which confirms that yes, right, we found the same answer 2 different ways, so that sure sounds like things are working. So that seems great. We have this recurrence relation that tells us about the time that it takes, the number of steps that it takes to solve the n-disk problem. And we could apply it to 8, right? We could compute 8 in terms of 7. In order to do that, we'd first have to find 7, so we'd compute that in terms of 6 and so on. Eventually, bringing this down to the case where we get, T2 and T1. But that is, although perhaps in some sense a solution, it's clearly an unsatisfying solution because it takes so long to compute it, basically. We would like to have a more efficient answer to the problem, right? We would like to have an answer where we could very easily and directly compute the answer for any choice of n. And so that's what we're going to discuss in the next video.